We are live. Welcome, Huntington Algebra students. Good to see you again. Whether you're watching this live or you're following up at a later time on the rewind, this week we are starting quadratics. And for some of you, that is completely new and foreign content insofar as your math experiences. So I think at least once a week from here on out, we'll be doing a little online lesson. Try and keep it informative, brief, and helpful to what I want you guys to do. Now, at the very end of this video lesson, there will be a 6-question assignment for you to do. That assignment can be done on paper and mailed in at the appropriate time, or you can email me the answers or take a picture of your work and send it to me. We won't, well, I suppose you could even upload it onto Google Classroom and allow me to view it. There won't be an assignment on Google Classroom other than the warm-up that was already posted. So if you would like to, I will give you about 15 seconds to grab a piece of paper and something to write with, because we will be going over a few things that you may want to write down. Granted, this video will stay up on YouTube for as long as YouTube's around, I'm imagining. So if you need to go back and look at something, you can do that as well. So without further ado, quadratic formulas or quadratic equations. Let me pull up my document camera. There are two most common ways that quadratic equations can be written. The first one is what's called standard form. Okay, and let me pull up my document camera. Okay. Standard form of a quadratic equation comes in the form of y equals, and then everything else is on the other side of y. Just like when we talked about equations for lines, y equals mx plus b. All right, now some of those letters are the same, some of those variables are different and have different meanings now in quadratics, but they always begin with y. Y equals, and then the rest of it. We want everything on one side of the equation and y on the other side. All right, so ax squared plus bx plus c is the generic version of an equation written in standard form, a quadratic equation written in standard form. We can also use function notation because quadratic equations are functions, meaning they pass the vertical line test, or there are no 2 points vertically stacked on top of each other at any point in the graph. And later on, this is a few lessons down the road, but they can also have 0 on one side and everything on the other. Now, granted, the y's, the f of x, and the zeros, they could all be on the right side too, but for consistency, we'll just put them all on the left for now. Now, there are some things about equations written in standard form that we can tell just by knowing what A, B, and C represent. A, B, and C, as this is written right now, again, this is the generic form. So A, B, and C will have numbers in them every time, even if those numbers end up being 1 or 0. They can be negative, they can be decimals. But knowing a few things about these variables, being identify what numbers represent A, B, and C, will help you get a better idea of what the graph of this function will look like. For example, all graphs of quadratic equations are going to be parabolas. Parabolas are U-shaped, essentially, except where like the capital letter U, the sides of the arms of the letter U end up being parallel to each other, a parabola keeps working its way apart from each other. They never work their way back to closer. They never intersect. They keep working further and further apart. And if they're downward, they keep working further and further apart, as the arrows would suggest. Okay, parabolas are also symmetric, which means they have a halfway point that you can fold over, and one side looks just like the other side. Okay? Couple of basic things here, and some of you guys know this already, and we've discussed a little bit about quadratics before, but now we're into a quadratics unit. Every parabola has what's called a vertex. A vertex, you can see, it's highlighted in red. I don't know if you can see that it's red, but it is at the top or the bottom of the parabola, depending on which way it's facing. Okay, and that point is where it transitions from going downward and hits this point and then begins its ascent. Or if it's a downward opening parabola, it goes from upward to then turning downward. It's a very important point in a parabola. The line of symmetry runs right through it. It's that midpoint on that curve, you could call it. Depending on if your parabola opens upward or if it opens downward, that vertex can be considered the minimum point in that case, or a maximum point in this case. A minimum just means it's the lowest, right? Minimum, that has an association to small or lowest. In this case, it's the bottom point. It's the point at which, you know, it starts to turn back upward. If it's a downward facing parabola, the vertex would be considered the maximum point, the highest point. All right, that's probably something that can be easily grasped, as long as you know what you're looking for. Now, A, B, and C. Getting back to these three numbers. There are some things that if you can identify what number A is in the problem, and if you can identify what letter C, we're just going to deal with those two right now. They're pretty easy to identify, even in different looking quadratic equations. A is always the number A is always the number that is associated with the x squared term, right? It's the coefficient for the x squared term. Now, the reason why A is important, or it can help us with its graph, is that A tells us if we have an upward facing parabola or a downward facing, should get on camera, or a downward facing parabola. An upward facing parabola, A is positive. If A is negative, then the parabola opens downward. And I like to think of that as, you know, if you're positive, you're happy, your smile is up. But if you're negative or you're sad, then your frown is down, right? Happy parabola, sad parabola. Positive A, negative A. Okay. That's it. That's what A can tell us, if it's upward or downward facing. And that's important because there's only two choices for parabolas, upward or downward. A will tell you that. C in the equation represents something that we know. The y-intercept. C represents the y-intercept, and it is the number that does not have a variable attached to it. So when you're looking at an equation, you know, and it's y equals, and then the rest of the quadratic equation that is there, the number that is not attached to a variable is your y-intercept. That's where the parabola crosses the y-axis at, whether it opens upward or downward. Every quadratic equation has a y-intercept somewhere. Every single one. Now, this is for later, but not every quadratic equation has an x-intercept or x-intercepts, because you can have one or two. All right. Now, what kind of a parabola, what would it look like on a graph if it didn't have x-intercepts at all? Do you know? Can you draw a sketch of that parabola that does not have, or that does not cross the x-axis in any way? Something like this, or, oops, forgive my parabola sketch. But a parabola that doesn't cross the x-intercept is just above the x-axis, or it's below the x-axis. Now, a lot of times they will have x-intercepts. They'll cross somewhere once or twice. But that's a little bit for down the road. Okay, and in fact, that's my little note down here. All parabolas have a y-intercept, but not all parabolas have an x-intercept or x-intercepts. Okay. On my next sheet here, right at the top, there are two equations written in what is considered standard form. That's weird. It was zooming in and out every time I moved my pen back and forth. Okay. Now, what we want to do here first, at least for our purposes today, is we want to identify what A, B, and C happen to be in both of these equations. Now, if you have paper and pencil, all right, I'd like you to just write down what you think A, B, and C are represented by in these equations. I will give you 10 seconds to put something down. Now remember, standard form, everything would be positive in the generic form. So if you get a negative number for A, B, or C, then that means A or B or C would be negative. So in this case, for the first problem here, A would be -3. B is -8. And C is 4. Okay? Pretty easy, transferable, A, B, and C. Keep in mind that these three things can be rearranged, but A is still associated with the x squared term. B is still associated with the x term. C is always the number that's by itself. So even if we were to rearrange these three terms, A, B, and C don't change. Okay? Important to note that. For the second problem, there are only two terms, but three numbers that we have to write down. In this case, there is no number for A. However, there is an x squared term there. It's like when we have a variable by itself, we don't say there are 0 w's. We say that there is 1 w. Writing a 1 next to a variable is a little bit redundant, and we don't need to do that. So in this case, there is an x squared here, but there is only 1 x squared there. So in this case, A is 1. In this problem, B is associated with the x term, and the x term has a coefficient of 6, a positive 6. And then C is not there. there is no number, and there is only one number that represents nothing, and that would be 0. Okay? So what have we done by identifying A, B, and C? Well, we understand that A represents whether the parabola opens upward or downward. So in the first problem, this is a downward opening parabola. In the second problem, A is positive. It is happy, so it is opening upward. All right? That doesn't help us necessarily put the parabola on the graph. It just gives us an idea that, okay, I'm dealing with this kind of a parabola or this kind of a parabola. Just to have an expectation when you do get to graphing what it should look like. All right? What I can also determine is that C, being the y-intercept, means this parabola is going to run through the point 0, 4, and this parabola is going to run through the point 0, 0. Okay? Now again, you can have an infinite number of parabolas that go through one point. All right? All we can tell for sure so far is that the first parabola opens downward and goes through 0, 4. The second parabola opens upward in some way and goes through 0, 0. Now, there is one. Oh, I guess I wrote that down for us to choose from. I'll just go ahead and put all that here. So what I had written down is, does it open upward or downward? Where's the y-intercept at? And I already wrote that down. I already forgot what I had prepared here. Okay, so the y-intercepts are locked and loaded here. Now, the last thing, and we haven't discussed it yet, but is this going to be a more narrow parabola, you know, a skinny parabola, or is it a wide opening parabola, whether it's opening upward or downward? And that you can tell by looking at the number that is in the place of A. So A can kind of tell you two things. A will tell you if it opens upward or downward. A can also tell you if it's going to be skinny or wide as far as what are the arms of the parabola doing. Are they narrowly increasing or decreasing, or are they taking their time to turn upward in the parabola? Well, the key is, as A gets bigger, the more narrow it gets. Because whatever your x term is, you're squaring it, right? So that means, like if we just start at 1, so if we just squared 1, 1 squared is 1. 2 squared was 4. 3 squared is 9. 4 squared is 16. So the difference between x and x squared, as you get bigger, the difference between the two also gets bigger. Okay? Now, if you're also then, after squaring a number, multiplying by a number, that is increasing the difference between x and y, in this case, or what you're doing with x. So that was going to make your rate of increase more the bigger A gets, because you're multiplying by 2, 3, or 4, or 5, or whatever the coefficient is. That's really rocketing upward or rocketing downward the difference between x and y. So the bigger the number, or the further away from 0 A gets, the narrower the parabola gets. Now, if you were to have like a fractional amount for A, that means whatever x squared is, you're going to, let's say A is 1/2. Then you're going to cut it in half. So then the difference between x and y is actually slowed down. It's half as much as what it would be normally. So it's going to really take its time to increase if you get a fractional amount. So the closer the number is to 0, like 1/2 or 1/8 or 1/25, it's really going to widen out. So for this first one, even though it's a negative number, it's -3. So that's going to make this parabola a bit more on the narrow side. And this is kind of objective too. If you just had x squared by itself, it's going to look a certain way. If you have a graphing calculator, even better, faster. Because you can graph anything, any equation using a t-table, but that can sometimes take time, and you guys know that. If you have a graphing calculator, it goes by a little quicker. And if you have questions on how to use your graphing calculator, hit me up. I'll help you out. But generally speaking, this first equation is going to be a little bit more on the narrow side, okay? Because -3 is a little bit further away from 0 than -1 is, or 1. This case, A being 1, it's not necessarily narrow or wide. It's what I don't know how you would describe it. Normal, average. Average probably not the best word, but we use the graph y = x squared as kind of how we determine if it's narrower or wider. What we mean is it narrower than x squared or is it wider than x squared? And so I guess if it is x squared, then it is just that. Maybe not a good example for that one. Moving on. I just wrote on a half piece there. And the nice thing about doing a lesson on a video is that you can push pause. You can write a couple things down. You don't even have to follow along as I'm speaking. You can just put pause. Maybe try the problem that we're talking about on your own first. Come back to it, check it, see if it lines up with what I'm doing here. Now, there is one other way quadratic equations are written, and that is using vertex form. Vertex form, and I'll write this here because I didn't pre-write it. Looks like this. Vertex form of a quadratic equation is not probably as common as standard form, standard being the standard. But when equations are written in this form, there are a few things that this equation can tell us that standard form doesn't tell us. So it has some applications that are helpful as well. You'll notice that A is being used in this equation, and it is still A. Everything that we used A for in standard form can also be derived using A in vertex form. A will still tell you if the parabola opens upward or downward, and A will still give you an idea if it's more of a narrow or if it's more of a wide opening parabola. So that part is the same. A is still A. Nice. Now, vertex form is called vertex form because the equation tells you where the vertex of the parabola is. That is awesome. That is a very helpful piece of information when going to graph your parabola. We don't know where the vertex is of an equation written in standard form. At least it's not immediately evident. Okay? The vertex of the parabola is found at h comma k. Now, h, k are in the equation. The numbers that are in h and k are the x and y coordinates for the vertex. Now, we couldn't use x again because we've already got an x, and we can't use y because we've already got a y. Too many x's and y's get confusing, even if we start labeling x1 and x2 and x3 and so forth, like in our slope formula from a couple months back. But the vertex of the parabola, remember, the vertex of the parabola is either the minimum or the maximum point. It's where the line of symmetry goes through. It is an important part, an important point in every parabola. So the fact that equations written in this form tell us that point is pretty handy. Okay, that's a difference. Okay, so we have a similarity between the two forms. A is still A in both forms, but here's the difference. Vertex form tells you the vertex, whereas standard form tells you the y-intercept. Okay, right off the bat, you know those things about each other. There isn't one that does them both together. However, finding the y-intercept in vertex form isn't too difficult to do. And I'll show you that here in just a moment. So if I give you two equations, all right, I should have wrote that bigger. It kind of looks like I don't know, maybe your screen's bigger than mine, but two equations here. And they're both written in vertex form. I'll give you a second to write them down. But here are the questions I'm going to ask you. Now, let's answer the second one first because we're familiar with it at least a little bit. In this equation right here, is this parabola going to open upward or downward? Is it an open upward facing parabola or downward? Well, A, the number that is in the place of A, happens to be a negative number. So that x squared term, if we were to multiply this all out, would end up being a negative x squared term. So this is going to be a downward opening parabola. For the second equation, what would A be in this problem? Okay, there is no number there. However, there is still this part, or the x squared part is still there. So that would mean A would be 1 in this problem. So 1 being a positive 1, this parabola is going to open upward. Okay, that's good. That's a little tidbit that's helpful. All right, now the vertex, the whole reason why we have this form of a quadratic equation. Vertex form tells us where the vertex is, the most important point on a parabola. It's our starting spot where we go to graph. So in this case, x minus whatever h is. Well, in this case, h would be a 2. The reason why we wouldn't put a negative 2 here is because it's already being subtracted. All right, we wouldn't, if 2 was a negative number, minus a negative would then turn to addition. Okay, and I hope that's not too confusing for you. But in this problem, our x coordinate for the vertex is just a 2 because we are subtracting whatever h is. And h in this case would have to be a 2 in order for it to stay subtraction. K, a positive whatever k is, all right, in this case it's 9. The vertex is at 9. Or excuse me, 2, 9. 2, 9. Over in the second problem, this reads x plus 5 squared minus 2. Now, the generic form, again, says x minus the h amount. Well, in the actual equation, we have an add 5. So what number could we put in for the x amount that would turn this subtraction to addition? Well, x would have to be a negative 5. Because if you subtract a negative 5, what you end up doing is adding 5. The minus and the subtraction turn it to addition. In this case, you know, k, if we have to subtract 2, then k would have to be a negative 2. Okay? This can be a little confusing, knowing when to switch your signs and when they need to stay the same. But if I can maybe shortcut this a little bit for you, K is always going to be the number that shows. H is going to be the opposite of the number that shows. You're going to see a -2 here, so that means it's going to be a +2. You're going to see an add 5 here, so X is going to be a -5. Okay, and again, that will be a little confusing at first, but as you do them, you'll figure it out. I have confidence in you. Can we determine whether or not this is a more narrow or wider? Well, again, by looking at A is -1/2. So we would consider this to be a little bit wider than normal. A is 1 here, so I guess we would consider that a normal width. Now, to find the y-intercept, remember the y-intercept has coordinates, has an x-coordinate of 0. Every y-intercept is on the y-axis. That means you're not going left or right anywhere. You're only moving up or down, which means your x-coordinate has to be 0. If 0, well, we're starting Tristan today. We're starting quadratics today, so you're all right. 0 has to be the x-coordinate. So if we just substitute in 0 for x and then solve whatever's left, y is going to be our y-coordinate. So -2 squared would be a +4. Half of +4, or -half of +4, is a -2 plus 9, and we'd get 7. Okay, so a little arithmetic involved to finding the y-intercept, but it's not terribly tricky because we're using 0. 0 is an awesome number to work with. 0 plus 5 is 5. 5 squared is 25. 25 minus 2 would be at 0, 23. Okay. So for these equations here, I mean, if we were just to graph what we know, for the first one, we know it opens downward, has a vertex at 2, 9, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, and has a y-intercept at 0, 7, 1, 2, 3, 4, 5, 6, 7. All right. We can sketch something like this. And we also know it's going to be a little bit wider, and that makes sense given what we know of the graph. For the second one, vertex at -5, 1, 2, 3, 4, 5, -2. It's going to open upward at a normal pace, and the y-intercept is going to be somewhere at 0, 23. So it's going to, if my graph was to scale, the y-intercept would be up here. It'd just kind of shoot up, something like that. All right. Now, this isn't incredibly accurate, but it does tell us bits of information about our graph. And even in standard form, actually, that's not the one. Even in standard form, we could still graph what we know, even though it's not as much. We could graph a vertex, a y-intercept that is narrow and opens downward, right? We don't know if this is the vertex, or maybe if the vertex is over here or something like that. Again, there's not a lot to go on graphing-wise when they're in standard form, at least not yet. And so it's a little bit more ambiguous of how it could look. in vertex form, we have a little bit more information, so we can kind of get a better idea of how these are going to look. Okay, I'm going to put up 6 problems for you to do. 3 of them are written in standard form. 3 of them are written in vertex form. And I'm going to ask you to write down everything that you can tell me about the equation as it's written, okay? Or the equation as it's written in vertex form. You know what? I'm actually going to do 8 questions because I wanted to try something else. So here, wish I could zoom that in for you. Maybe you can push pause and zoom it in on your phone. I'm adding 2 more here, and that's just because okay. They are a little bit shorter problems, the 2 that I added, but 8 questions. This is your assignment this week, guys and gals. So hopefully you're able to follow along. Shoot, I'm over half an hour. I wanted to be under half an hour. But this is your assignment. You can push pause on this and write them down on your paper if you want. And then again, you can mail them in when it's time to mail things in or drop things off, I'm sorry. Or you can take a picture of your work and email it to me. Or because I would like you to include a sketch based off of the information that you know. And I, again, understand that some of the information is incomplete, but based off of what you know, does it have a vertex? Does it have a y-intercept? I mean, they do have y-intercepts. Can you tell where the vertex is? Can you not? Does it open upward? Does it open downward? Is it going to be a little skinnier, or is it going to be a little wider than normal? You can tell me everything that you can about these equations in standard form and these equations in vertex form. And then at the end of it, include a sketch of what the best you might think this would look like if we actually labeled points, figured out a bunch of points, and graphed it. Okay? That's your assignment for the week, or that's your assignment for this lesson, which is for this week. And if you have any questions, please revert to this video, or if it's specific questions, you can email me or message me in Google Classroom. Thanks for following along. And what does the sketch mean? I mean, I want you to make a little graph and draw a picture of the parabola as best as you are able to, given the information you found. Okay? That's what I mean, Wyatt. Thanks for your question. I'm about to shut it down. But I'm going to pull myself out of the screen so that we can get a blown up version. And I'll leave it up here for just a minute so you can either copy it down or push pause and copy it down. So good to see you. Let me know if you need some help. Talk to you soon.